Programming is not always about telling the computer step by step what to do. Sometimes it's about describing the world in terms of facts and rules and letting the computer do the reasoning for us. This style is called logic programming. It's declarative, not imperative. Instead of giving instructions, we declare what must be true and the system figures out the rest. To see why this is powerful, let us try a classic challenge. We will take a puzzle and see how different it feels to solve it in imperative style versus the logic programming style. Here is a puzzle for you. Imagine five families live in five houses in a row. Each family is from different state. Kerala, Gujarat, West Bengal, Tamil Nadu, and Punjab. Each has a different profession. They celebrate different festival and prefer a different vehicle. Your challenge is, can you figure out exactly who lives where, what they do, what festival they celebrate, and what vehicle they own? Does it sound simple? Wait till you see the clues. Here are the clues or constraints. First, the Kerala resident lives in the first house. Second, the person who celebrates Onam is an engineer. Third, the farmer lives immediately next to the person who drives a scooter. Fourth, the person who drives an auto celebrates Pongal. Fifth, the teacher does not live next to the engineer. Sixth, the Tamil Nadu resident lives immediately left of the person who celebrates Durga Puja, and so on. There are 13 clues in total. And the question is, given these constraints, can you find out the complete arrangement, who lives where, who celebrates which festival, and who drives what? Let us see how this puzzle can be possibly solved using an imperative approach. Say in Python, we would write four nested loops for states, professions, festivals, and vehicles. We will have to generate all permutations and then check each clue one by one with if statements. That's hundreds of lines of code, messy conditions, and extremely inefficient. Sure, you can prune early, but now you are writing complex logic just to manage the search. So the problems are, this is very verbose in nature. We are explicitly writing whatever is required to be done, and it's very slow and inefficient. This is also very error prone, and finding mistakes in such program is going to be difficult. Can we use a different paradigm to solve the puzzle? Yes, we can use declarative programming. In contrast to this imperative style that we have just seen, declarative programming avoids all of that. You focus on what is true, the system figures out how to search. Instead of solving problems step by step, like we usually do in Python or C++, we will look at a style where we just state the facts and rules and let the computer do the reasoning for us. Along the way, I will also show you why declarative programming, saying what you want, is very different from imperative programming, saying how to do it. And we will see how powerful this can be. But why logic programming? Now, here is the challenge. If you try to solve this puzzle in the usual way with brute force technique, it explodes very quickly. Think about it. For five houses, if you try every possible ordering of states, that's 5 factorial, which is equal to 120 possibilities. Now multiply 5 factorial for professions, 5 factorial for festivals, 5 factorial for vehicles, etc. We are already talking about more than 600 million possibilities. No human is going to check that by hand. And even if you write imperative code, nested loops, and if condition, it becomes messy, slow, and hard to read. But with logic programming, we take a different route. We just declare the rules, which is going to look exactly the way the puzzle is stated. We don't tell the computer how to search. We say, person from Kerala is in the first house, the person who celebrates Navratri is an engineer, and so on and so forth. And then we ask Prolog, find me a world where all these rules are true. That's it. That's the declarative mindset. Here is the Prolog code. Notice how the code almost looks like the English text of the puzzle. Okay, let's walk through the heart of the solver. This clause begins with predicate head solve houses. That means when we ask solve H, Prolog will try to build a houses value that satisfies the constraint which are given below. Next, we immediately say that my houses is a list of five different things: H1, H2, H3, H4, H5. This creates a list of five positions, one term per house. Think of H1 through H5 as five empty boxes we will fill with house facts. This is unification. Houses become the five element list. Then we have four permutation calls, one for each attribute. So we have first for states, which is S1, S2, S3, S4, S5 is a permutation of Kerala, Gujarat, West Bengal, Tamil Nadu, and Punjab. Second, we have permutation for profession. So we have PF1, PF2 up to PF5, which is going to be a permutation of teacher, engineer, doctor, chef, and farmer. Same goes for permutation of festival and vehicles. What permutation does is it generates an ordering of attribute list and put the result in right hand list of variables. For example, S1 becomes state for house 1, S2 for house 2, and so on and so forth. So after these calls, each SI, PFI, FI, and VI is bound to one concrete element, but in all possible ordering as Prolog searches. Finally, we create actual house structures. H1 is equal to house, which has a number 1, and whatever binding we have got from the previous solution, previous part, S1, capital S1, PF1, F1, and V1. Same goes for H2, H3, etc. Finally, up to H5, which is house number 5. So each house has a position, has a state, has a profession, festival, and a vehicle. This packages the attributes for that slot. So now houses is a concrete list of five house systems ready for constraint checks that come next. So note that the equal to sign that we are using here is not same as what we use in other imperative programming language. Here, this equality is unification. We are binding terms. We are not doing arithmetic assignment. Why use permutation? Because it enforces that each attribute appears exactly once across the five houses. It naturally captures all different behavior without extra code. The order of putting this constraint is extremely important. If some constraint can be put early, we should be putting that because it's going to prune out the alternative to be explored. Otherwise, delaying is going to take into account more possibilities. So you can imagine one solution that Prolog might try is that S1, S2, S3, S4, 5 is equal to Kerala, Gujarat, West Bengal, Tamil Nadu, and similarly for professions, etc. So that's the setup. We created five slots, generated every legal assignment of four attribute classes, packaged them into house terms. Next, we will put constraints that we have for the puzzle. So now comes the encoding of clues as constraints. So the first constraint that we had was the Kerala resident lives in the first house. So we are now saying that H1 has to be binded with house where the house number is 1 and the second attribute which we have reserved for the state is Kerala. Rest of the things we are saying we don't know or we don't care at the moment. And the second constraint is the person who celebrates Onam is an engineer. So we want houses list to have a value which is house having engineer and Onam attributes together. The third constraint that we have in our problem is the farmer lives immediately next to the person who drives a scooter. So we are now using another predicate which we are going to define later. And what we want in is that in this houses list, the house of a farmer is next to the person who is owning a scooter. So these two things must come side by side in houses. We'll see in a minute how neighbor is defined. The next constraint is very similar to what we have seen earlier. The person who drives an auto celebrates Pongal. So this again, Pongal and auto should be together in house attribute. So the fourth constraint is the person who drives an auto celebrates Pongal. Now this is similar to what we have seen earlier in case of rule number 2, that we are going to make use of member predicate or relation, and we are now asking that houses must have a house where Pongal and auto are in the same box. Next, we have constraint the teacher does not live next to the engineer. Now, this symbol that we have used is for not. We are asking that house of teacher and engineer in this particular list should not be side by side. We will see later how neighbor is defined. The next constraint is the Tamil Nadu resident lives immediately left to the person who celebrates Durga Puja. So we are using a relation left of, where we are going to say that the person who is from Tamil Nadu is on the left side of person who is celebrating Durga Puja in this particular list houses. The constraint, seventh constraint is the person who celebrates Onam rides a bicycle. This is similar to what we have just seen earlier, Pongal and auto. So we are going to make use of the same predicate or relation, and we are stating a similar property here. The rule number 8 is the person who celebrates Vaishakhi lives at one end of the row. So that means such a person should have house number either 1 or 5. The rule number 9 is the chef lives immediately right of the Gujarat state. So we are now defining or creating another relation, right of, where we will say that this particular first thing is on the right side of the person who is from Gujarat in the list houses. And the constraint number 10, the West Bengal resident drives a car, is very similar to what we have seen earlier. Earlier we had festival and the vehicle associated. In this particular case, the state and the vehicle are associated. The person who celebrates Durga Puja does not live in the first house, is the next rule. So we are now saying H1 should not be binded with house number 1, where the binding of the festival is Durga Puja. Rule number 13 and 12 are very similar to what we have seen earlier. In 12, we are again asking the two persons to stay side by side. And in rule number 13, we are saying that the Punjab resident rides a bike. Now, given all this, we have, of course, made use of some predicates which we are required to define. So, neighbor predicate is very easy. When do we say A is neighbor of B in houses list? We look at the position of A in houses. We look at the position of B in houses, and we take the difference. So the difference should be either 1 or -1. If the difference is more than 2, then naturally they are not neighbors. Then we have this left of. So when do we say the first thing is on the left side of right? We again make use of the position nth1 predicate, and we are getting the position in pause L, and we are getting the position of right in pause R. And if you add 1 to the pause L, you must be able to get pause R. Then only we'll say that the this left is indeed on the left side of right. Right off is same as left off, because we can make use of left off by swapping left and right, and we can get the result for right off also. So given all this, we have now completely defined the puzzle and see that it's exactly similar to what the English text that we had for the puzzle. So let us solve this puzzle using Prolog. I've already put the program that I've just shown you in puzzle.pl file. So I'm loading it in SWI Prolog. And now I ask to solve and give the value for the houses or the list that we have just defined in our program. So when I do this, you can see that within a second, I've got my result that the possibility of this list is that the first house is owned by a Keralite who is an engineer, and he celebrates Onam and is owning a scooter. In the second house, a Gujarati person stays. He's a farmer and he celebrates Navratri, owns a bicycle. And similarly, in the fifth house, a Punjabi person stays. He's a doctor. He celebrates Vaishakhi and he owns a bike. If there was another alternative, system would have produced another alternative. But in this example, there is no other solution available. When we ran the solver, we got a neat, unique solution in just seconds. Imagine trying to check all 600 million possibilities manually. It would be hopeless. Prolog does it effortlessly because it's built on constraints and backtracking. Why is this so powerful? First, the code is almost identical to the natural language puzzle. That makes it very readable. Second, constraints prune impossible cases automatically. We don't need to write extra checks. Third, it's easy to modify. If I change a rule or a clue, I just change one line in my program. Finally, it scales very well. Add a new attribute like favorite dish, add 5 values, and Prolog still handles it. This is what declarative programming gives you: clarity, correctness, and power. So, what have we seen? Declarative programming means say what is required, not how to be done. Logic programming with Prolog uses unification, backtracking, and constraints to solve tough problems. Puzzles that look impossible by brute force become elegant in just a few lines of declarative code. Here is an exercise for you. Modify one clue, for example, instead of Vaishakhi at one end, say Vaishakhi is in the middle house. Then rerun the solver. What happens? This way, you will see just how flexible declarative programming is. If you enjoyed this puzzle, try encoding your own logic riddle. It's a fantastic way to learn declarative thinking.